siglo aportando al desarrollo social e industrial de Chile. Un siglo liderando la formación de ingenieros e ingenieras para un nuevo mundo. 9 departamentos académicos gestores de conocimiento para la sociedad y los sectores productivos. 11.000 estudiantes. 15 ingenierías civiles acortadas a 11 semestres. 8 ingenierías de ejecución. Universidad con 7 años de acreditación. 72 laboratorios de alta tecnología. 10 programas Centro de Investigación con Impacto Territorial. 12 programas de magíster. 4 programas de doctorado. 391 convenios internacionales. Centro de Innovación con tecnología única en Sudamérica. Perfil de egreso internacional, el sello USACH que soluciona problemas reales de las personas y se compromete a seguir fortaleciendo el desarrollo del país. Ya es un siglo y así seguiremos. Aportando a la ingeniería del futuro.
Good morning, everyone here in the audience. Buenos días, estudiantes de la Universidad de Santiago de Chile, de la Facultad de Ingeniería. ¿Qué más para los estudiantes de la Universidad Pontificia Bolivariana? Guten Tag for the students in the Fachhochschule Münster. We're here today to present the keynote lecture on global change. Here with us is Dr. Reinhard Job. He is the Dean of the Department of Electrical and Computer Science, and he's going to be giving a talk with our Director of the Electrical Engineering Department, Dr. Héctor Chavez. So welcome, Dr. Reinhard.
Okay, thank you very much, René. So, hello everybody. Thank you very much that you give me the opportunity to be here in this audience. Hello to everybody in the internet. Unfortunately, I cannot see you, but I hope you can see me and you can hear me. So I would like to give you a very brief keynote on climate, resources, and the environment. It's a very complex and big item, so I really can focus here in this time on a very few points, just to start. So when I started, when I was a young man, when I started to learn and to study, I was very enthusiastic with technology. Meanwhile, I'm becoming older, and at some points I have my doubts. So I will discuss this a little bit. So let's say my attitude is a little bit negative, and hopefully my colleague Hector after this will give a little bit positive opinion about the future. Okay, we will see. Next one, please. So this is the outline of my presentation. I will focus on 3 key points. This is climate change, shortage of resources, and destruction of the environment. And finally, I call it discussion. These are a few thoughts about the future, what can be done to overcome our problems, and it is somehow the link to the next presentation of Héctor Chavez. Next one, please. So we start with climate change. Okay, so climate change, in fact, is not really a new phenomenon. During the periods, during the various periods and ages of our planet Earth, we had a lot of climate changes, and here you see a graph that is documenting this for the last 400,000 years. What you see here in this graph, we concentrate on the 2 upper graphs. The blue one is the CO2 concentration in the of roughly 400,000 years. So, and you can see that the temperature changed from -8 to +2 degrees C where 0 means the pre-industrial value, let's say at a time of about, let's say, 1750. So, and over this period, over these hundred thousands of years, this what the people call natural climate changes. So what does it come from? In fact, it comes from the rotation of the Earth around the Sun. So it's an elliptical path, not a circular one, it's an elliptical path. And this elliptical path somehow is disturbed by the other planets. And also we have the rotation axis of the Earth is not perpendicular. If here's the Sun and here's the Earth, and the rotation axis of the Earth is not perpendicular, but is somehow tilted, and it also moves like this. Yeah. So, and all these path parameters undergo some variations, periodical variations with different periodicities, changing between a few years up to thousands of years, and they are overlapping, and all these things can be calculated. This was done by a scientist from Serbia. These are called the so-called Milankovitch cycles, and by this so-called Milankovitch cycles, you really can well understood these variations in the CO2 concentrations, in the methane concentrations, and then finally the temperature variation, in the global temperature variation over the periods of the year. So from where we know it? We know it from ice core data. You drill holes in the ground, for instance, in Antarctica, in the glaciers, and there are small bubbles of air inside. And this can be analyzed, and the deeper you go to the depths, the more the farther you go in the time. Yeah. So and also the temperature you can estimate from these analytics, since the concentrations of certain oxygen isotopes are strongly related or directly related to the average temperatures. Yeah? So this is well understood, well known, and well documented. So this is climate change, natural climate change, and this is a good one. Yeah, and please the next one. So what has changed? This is a graph, a very beautiful graph from the NASA. So here you see these variations in carbon dioxide, which is finally could be explained by the Milankovitch cycles. Yeah, and here we see a period of 800,000 years, so nearly 1 million years, and there was no strong changes. The highest point that was ever measured with the CO2 concentrations in the atmosphere was roughly 330,000 years ago, and it came close to 300 ppm. But then, very, very, very recently, something dramatically changed. Yeah? Here, suddenly, during the last years, CO2 concentration dramatically changed. It grew up. In 1950, we had here this position, and we exceeded for the first time the level in the atmosphere that we had for the last roughly 1 million years. Yeah, so this is a dramatic change, and especially since it occurs in such a very short time. Very short time, if you think in geological periods. So, and this is in fact a really completely new situation. Please. So here I have a very famous curve. It is measured on the Mauna Loa volcano on Hawaii. and it documents for every day the CO2 concentration in the atmosphere. It is done at about 3,400 meter elevation on the volcano. The observatory where it is measured is located on the western side of the Hawaiian Islands. The next, islands where people are living, where industry is located, is in Japan, quite far away. So these are really very clean measurements. They are not disturbed from anything. And since there's a steady western wind, so very clean data. And you see they started in 1958. It is the year of my birth, and it is steadily increasing. So I'm always joking, since I was born, the situation became worse. So, and what you also can see here, the red curves are the annual variations. So if it is warmer, you get more CO2 to the air and so on. And the black one is an average line through this. So we are of course, we know this phenomena since a lot of years. We are discussing this, the politicians are discussing this, the scientists are discussing this, and we are speaking a lot about things, how to avoid this, to reduce this, blah, 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 blah. What is happening, if you look at the curve? Nothing. Yeah? So this is a real problem. Please, the next one. This curve shows the methane concentrations. It is measured over a global network around the globe. And this curve, from my point of view, is a shocking one. CO2, we know nothing is happening, but this curve, from my point of view, is really shocking. They started a little bit later than the CO2 measurements. So the curve is going up. And CO2 is also a strong climate gas, yes, I have to add. So and somehow, okay, so around the year 2000, it seems that it came to a saturation. But recently, from the midst of or let's say of this period between 2000 and 2010, something like here, 2005 or so, it's going up again, and it has a positive curvature. So in fact, what we see in the methane concentration in the atmosphere is somehow a kind of exponential increase. And what is it? From my point of view, it seems that in the last years, in the last decade, somehow we have crossed the first tipping points. Yeah, and okay, it's not absolutely clear now, but if I look at the curve, what could be an explanation for this, that we already see here the beginning of the melting of the permafrost. Yeah, and this, in fact, is really dramatic, since it's hard to believe that somehow we can stop this in the future. Yeah, next one, please. So, one big point, which makes us somehow fear is this for the future is a climate change. The next point is a shortage of resources, please. So this is a nice curve I found in a book, something like, when was it? More than 10 years ago. It was a book on material science, and it's a very interesting graph. You see here on the x-axis, you see the dependence on non-renewable materials of our societies from 0% to 100%. And on the y-axis, you see a time scale. Yeah, it's not linear. So this is 100,000 years below Christ, 10,000 years below Christ, 1,000 years below Christ. And then here it's becoming shorter. Here's 1920, 1940, 1960, and so on. So what you can see in this curve, up to about the year 2000 below Christ, something like here. In fact, those communities, those societies, practically only used renewable materials, like wood, maybe a little bit gold was used or something like this, what they found, but it doesn't matter. Yeah? Then between the year 1000 below Christ and 1000 after Christ, we had a slight increase of non-renewable materials. So, okay, more and more metals were used. Basically, these are the metals. Yeah? So this is a period here. And then it changed dramatically. After the year 1500, and especially after 1850, we have a very, very strong increase of the usage of non-renewable materials. And we can say since about 1960, so again, starting with the beginning or nearly with the beginning of my life, we had de facto 100% dependence on non-renewable materials. Please. So, of course, we are very strongly dependent on raw materials, and since the beginning of the Industrial Revolution, the consumption of such materials have increased dramatically and steadily, as we have seen. So we need a lot of natural raw materials, for instance, ore, minerals, fossil fuels, and so on and so on. And this is either directly used for materials and raw materials, or it is used for the production of energy to produce substances, materials, and raw materials for further usage. Yeah? So, and up to about the midst of the 20th century, the consumption of raw materials was always smaller than the discovery of new deposits of raw materials. Typical example is oil. Yeah? But since the year 2000, roughly, this does not apply anymore. And this is a strong change. Yeah? Please, the next one. So, what we can say at this point, since the beginning of the industrialization, so since the beginning of the, let's say, roughly the 19th century, I have emphasized that the humans used more and more raw materials, especially the consumption of non-renewable raw materials increased dramatically. So, and at the end of the 20th century, we can say that these non-renewable materials have practically completely replaced all renewable raw materials. So in fact, as I said, by this nice curve, I showed you a few slides before, in fact, we have a total dependency on non-renewable materials. So what does it mean, total dependency? In fact, it's a kind of addiction. Our societies are addicted to non-renewable materials, and if you are addicted to something, like with drugs, you cannot live without it anymore. Yeah? So we can say our modern industrial societies are addicted to a lot of raw materials, non-renewable raw materials, like oil, cobalt, tantalum, etc., etc., etc. Please, the next one. So the very good example is the example of oil. Yeah, so it's a famous peak oil dilemma. I would like to introduce Mr. King Hubbard. He's a US geologist and a geophysicist, and he was an employee of the Shell company. Later, he became a professor in Stanford and Berkeley, not Steinfurt. So what did he do? He predicted that at this time he was a senior scientist at Shell. He predicted that the global oil production has a maximum. Yeah, he did it in the 50s, and here's a curve. Later, when he was already a professor, he wrote a book on this. And for two basic, two boundary conditions. He said that the overall oil on the ores can be to a lower level to about 1.35, 10 to the 12 barrel of oil. Barrel is something like 150 liters. And or the upper boundary could be 2.1 times 10 to the 12 barrel. So for this, between these two barriers, he calculated the production of oil in 10 to the 9 barrels per year. And he saw that a peak appeared. And so this was the old data. So and for the lower boundary, the peak should appear already well below the year 2000. And for the upper boundary, the peak should appear at about the year 2000. Yeah? So then you had some periods of time where you really can produce oil to a large extent. So these are these boundaries here, 80% usage for the lower boundary. It is 58 years. For the larger value, it is 64 years. Yeah. So okay, he predicted it. His bosses at the Shell company were not very happy with this. Yeah. At this time, he was working, as I said, as a senior geologist for Shell, and in the US there was a lot of oil production in Texas, as you know. Yes, and okay, they threw him out. Yeah, of course, but he was right. Do you find a lot of oil nowadays in Texas? Not so much anymore. Yes, they throw him out. He became a professor and so on. Please, the next one. There were after this. So this was the initial study. After this, a lot of studies were done, either by oil companies like British Petrol and a lot of other institutions made such studies on peak oil. And what you can see, somehow all these studies give a value that around the year 2010, somehow a peak should occur. Next one. So, but oops, it's 2025. So we are already above the mountain. And we can say, and meanwhile we also feel it somehow, that the peak oil is a caesura for our industrial culture, since most of our, or a big part of our energy production, our mobility and so on, depends strongly on oil. Next one, please. So, but we can extend these ideas, yes, and in fact what we have nowadays, we have a peak of nearly everything dilemma, I call it, yes. We are dependent on a lot of critical raw materials to build all the nice things what we have, like our smartphones, Eckhard Finkel's camera, and so on and so on. And here and you see some examples here on this graph. For instance, China, again, we also have some political problems with these things, yes, especially the rare earth metals, what we use for a lot of things. And in Russia, we have the platinum group metals. And in Europe, with Russia, we have a slight problem, and so on, yeah. And please, next one. So let me give you another example. For instance, I just said peak of nearly everything dilemma. Let's look at peak copper. Yeah, there also a similar situation occurs. It extends a little bit more longer to the future in comparison to the oil. But here you see for various countries where copper is produced. Chile, for instance, here this olive green part, you see somehow at around 2040 or 35, a peak copper could be expected. If it comes 10 or 20 years later, in fact, it doesn't change a lot. Yeah, please, the next one. This is another example, peak cobalt. And very often we are thinking, okay, it doesn't matter, we make recycling, no problem. But if you look here in this study, the peak copper was studied, and recycling was introduced. And what you can see, in fact, recycling does not change very much the situation to the positive. So, and in fact, it's quite simple. If you think about aluminum, aluminum is one of the metals which can be very, very easy recycled technologically. This means 90% or even somewhat more can be recycled. Let's say 90%. So what happens? You drink a can of Coke, it's over, you throw it away, it's recycled, you drink the next one. How often you can drink such a Coke before the aluminum is gone? It's roughly 10 times. Roughly 10 times, yeah? So from this point of view, recycling, somehow it shifted the situation somehow, but not dramatically. We are speaking about decades, not about centuries, yeah? Yeah, this is the point. And why is it so? It's simply basic physics. Yeah, it's simply the second law of thermodynamics. It's simply the entropy, which somehow rules us completely. And this we cannot change. Very simple. The next one, please. So these were my brief notes on the shortage of resources. Let's come to another point. About this, we can speak maybe 10 hours. I will only give a very few examples. Please, next one. So we speak about the destruction of the environment. It's a graph. It's quite old already. It's from our famous weekly newspapers, Zeit online. Somebody who was in Germany maybe knows this. So this graph shows that the production of plastics material, polymers in fact, is strongly increasing over, again, the last 50, 60 years. Plastic is used usually for short-living consumables like plastic bags, like a box for yogurt, what we had in the morning for breakfast, and so on and so on and so on. Usually packaging materials, products for one-time use, etc. So, and you see there's a really very strong increase of this plastic production, and in fact, this plastic is the epitome of a not sustainable economy at all. Yeah? And we know today that the amount of plastics, if we think about the weight, plastic is a rather light material usually. If you consider the amount of plastic production nowadays with regard to the weight, it is more than the production of steel, which is quite heavy material. Yeah? Next one, please. So, and yeah, what does it mean? Yeah? Here's a graph that somehow documents the pollutions of the oceans everywhere on the world. And here we see the so-called drift currents of the oceans. Yeah, so the ocean somehow undergoes such cycles of drift currents. Yeah, this is well understood. And so if plastic waste via our rivers and so on somehow is flooded to the oceans, for instance here, who we can blame a little bit, let's blame China. China puts a lot of plastic via its oceans to the seas, and due to this northern Pacific drift currents is driven around. Maybe you also can blame a little bit Chile. You put your plastic into the southern Pacific Ocean, and somehow it is also wandering through the ocean via these drift currents. And let's look on some examples. For instance here, this is washed up garbage at an Hawaiian island. Hawaii somewhere is located here, in nearly the middle of the Pacific. So this is not waste from the Hawaiian island itself, it's simply washed up. Yeah? What else do we have? Here we have plastic waste on Henderson Island. Henderson Island is an island which is in the middle of nothing. It's somewhere lying between South America and New Zealand in the middle of nowhere. Yeah? So, and okay, here you see some remains of a dead albatross, some bones here, albatross bones, and with a lot of plastic in it. In fact, this bird ate plastic and he died from it. Okay, not very funny. Please, next one. Another point is the reduction of the oxygen concentration in the oceans, and this is a very, very, very serious problem. Maybe it's even worse than the CO2 or methane concentrations in the atmosphere. Well, what we can face during recent decades, that the average oxygen concentration in big parts of the ocean are reduced. So, and here's an example. It's again a figure from the NASA. It's North America. It's the Gulf of Mexico, and here the red areas. This is I don't know, the plankton bloom. You have the water is warm. The ocean is not so deep, and through the rivers you get a strong impact of nitrites into the ocean water, and then you have a plankton bloom, and in fact this is not very healthy. In principle, here these parts near the coast are in principle a dead ocean. So what do you have in such regions? Such ocean regions release dinitrogen oxide, N2O, which is a very effective and strong climate gas. Yeah, and okay, usually always some dinitrogen oxide is evaporated from the ocean, but in such regions which are dead, it can be 10,000 times higher. Yeah, and N2O is a very strong climate change. And meanwhile, we have a lot of regions, for instance, in the Red Sea, between Egypt and Arabia, there are strong parts which are nearly completely dead. It was a paradise for scuba diving, or still it is, but I'm sure not for a long time anymore. Please. So let's come close to the end and do a little bit discussion. Please, next one. So I would like to start with a question. It's my question number one. Do modern societies have a real problem with the supply of energy? So either if we think about the classical carbon energies, coal, oil, and so on. Okay, with oil, it's becoming a little bit, as we saw from the peak oil phenomena, not so much anymore. But if you think about coal, we have a lot of coal. Yeah, we have enough coal for the next 300, 400 years. No problem. But if we fire this, we also can kill ourselves directly due to the climate change. Yeah. So, but please, next one. But of course, we have an alternative, and these are the renewable energies. Yeah. So this is a good part of my story. Yes. What is renewable energy? Renewable energy means inexhaustible energy resources for human time horizons. Okay, this is basically the sun, of course. Solar energy, which provides us with a lot of energy. We also have geothermal energy. What is the heat inside our planet? In fact, it's a remnant energy from the time when our planet was more than 4 billion years ago. We had cosmic dust. Due to gravitation, it somehow collapsed and forms our planet. So this is a very brief story how it's happened. So potential energy is transformed to kinetic energy and finally to thermal energy, and still inside our planet we have this thermal energy. And we also have a lot of nuclear isotopes, and they also heat up within our planet and provide us with geothermal energy. And we have planetary energy. In fact, this is the effect of the moon, the tides, and of course also from other planets, but the effect of the moon is so strong that the others don't play a role. Please, the next one, there are some numbers what we have. Okay, and before I come to the next slide, just 1 point. So we have the sun, we have the moon and the planets, and we have the Earth itself. Solar energy, tides, geothermal energy. And what the sun delivers is not only solar radiation or solar heat, but there's also some indirect solar energy. This is, for instance, water flow, rainfall. The oceans are heated up by the sun. We have the clouds, they are going to the land. We have rain, the water is flooding back via the rivers to the oceans, and then we can use the water for energy production. Yeah? We have ocean currents, we have wind, also indirect solar energy. We have waves, and we have biomass. Yeah? So, and we have also, so this is a natural transformation, but we also provided now, meanwhile, we are quite good in this. We have a lot of technical transformation. We know how to use photovoltaics. We have some effective solar thermal collectors. We have solar off. We have wind power plants, and so on and so on and so on. And finally, via this transformations of energy from the sun via the natural transformation via the technical transformation. Finally, we have the energy, what we need. What do we need? We need current, electricity. We need somehow fuel for driving, and we need heating when it's becoming cold. Yeah. So this we have already. Please, next one. And so, as I said, we have a lot of energy. On the right side, you see as a bowl, so these are bowls, three-dimensional. We have the amount of coal what we have the amount of oil, we have the amount of gas, and we also have the amount of uranium if you want to build nuclear power plants. Here, this small bowl, it represents the annual demand of energy of the Earth. Yeah? So we can say, okay, we have here quite a lot of classical energy sources, but of course they are decreasing with the years. On the left side we have the sun. Yeah, this is the energy ball, three-dimensional, the solar energy which comes to the Earth, and every year steadily. Yeah, and we have the indirect solar energy like wind, like biomass, usable water energy, and so on. So this is steadily delivered. Here we have this small ball is the planetary energy. These are the tides, in fact. Only with tides we could not, we don't have enough energy to support us in our actual style, but here the rest should be no problem. Next one. So, do modern societies have really a problem with the supply of energy? Next one. My answer is definitely no. Next one, please. But we can ask a second question. Can we provide, let's say, the actual Western style of living in a sustainable way for all people on Earth? Next one. And my answer is, I have my doubts. I even can express it stronger. I also could have written here a definitely no. And why is it so? Since to provide all this technology, also renewable energy technologies, we need the material to build the things up. And for this we need the resources. We need these metals, yeah, and also these metals what we need and so on. We have, as I said, the peak of nearly everything dilemma. Yeah, this is the point. Yeah, and this makes me skeptical if I think about the future. Next one, please. So I would like to end with some final remarks, and I will quote one of my big heroes, Albert Einstein. We cannot solve our problems with the same thinking we used when we created them. Yeah, this is a very strong point. And so somehow we entered a one-way road, and at the end it stops. We cannot continue, and somehow we have to learn how to come back and find another way. Yeah, so this is, I think, what Einstein is. But let me give another, please. There's another quote of Einstein, this I also like very much. Two things are infinite, the universe and the stupidity of men. However, in the first case, the universe, I'm not really sure. Okay. That's it. Thank you very much for your patience. Thanks a lot. Any questions? Otherwise, I don't know. I think now it's your turn, or?
Sorry, just a quick question.
Yeah.
So what do you think it's, you're picturing as a big problem, right? So what's the role of engineering in that?
Okay, I think the role of engineering is that we somehow can help that the problems will become not too bad. Yeah, I mean, we speak about natural sciences, we speak about somehow about engineering and so on. Definitely, at this point, we did not speak about politics. Of course, one also has to speak about politics. And in fact, this is the main point. So somehow we have to work globally together. And of course, we cannot avoid some things. I don't think that we can stop the increase of the temperature to this 1.5 degrees C point. I think we are already above it. But somehow with technology, we can try to help to overcome with these problems. Yeah, of course, we have to stop the carbon industry as soon as possible. Yeah, and engineering has to concentrate on the renewable energies. Yeah, in fact, we have to stop to invent senseless technology. Yeah, a smartphone. Is a smartphone useful for the future problems? I think a smartphone is a typical thing. Everybody has it. I also have one. Only Eckhart has none. His one was stolen in the subway. Yeah, if we waste our resources for senseless technology, then we get a problem. Yeah, if we build such phones which has an average lifetime of 2 or 3 years, and then they are thrown away. Yeah, and recycling is a problem, as I said. I mean, we should take these resources better for other things, to build windmills or such things. Yeah, this is my point. Since all our resources are limited, we only have one planet. Yeah, the actual lifestyle in Germany somehow needs 3 Earths. Yeah, we have other countries like, for instance, in Arabia, Qatar. Their lifestyle, they need 8 or 12 Earths. I don't know exactly. Also Australia, they also need much more. Yeah. Here in South America, the situation is better. The societies are poorer. They don't use so much materials. And you have everything, of course, has to be somehow normalized to the size of the country. Yeah? Germany is small. We have a lot of people. We have a lot of technology. We have too much money. And we spend our money too often to senseless things, for senseless things. This is my point. But engineers, somehow, we have to teach our students to concentrate on the technology which is useful, not to the technology which is senseless. Yeah. I mean, I'm also a boy, and when I was young, I also liked cars. But does it make sense to build a Porsche with 500 PS driving 320 kilometers per hour? Definitely no. Then we can say, oh, we build electric cars. Yeah, okay, let's develop a Tesla. But does it make sense to build? Friends of mine, they bought a Tesla 2 years ago, 460 PS. This car is driving, I don't know, 260 kilometers per hour. With an acceleration faster, higher than a Porsche. Does it make sense? Is this renewable energy? Definitely no. Yes, so we have to think about to develop things which last long times, which are more simple, which can be easily repaired, and so on. Yeah, this is my point. And who should this do? Only engineers can do it. So I think our profession is very important for the future, but somehow we have to shift it our mind. Jörg.
But what you're describing, saying we have to develop things which we use for a longer time, which are more simple to replace. If I look at our history, we had that already. We had simple things and we used them for a very long time because we had nothing.
Yeah.
So we had it already. So would it be kind of clever step back to that time?
I don't think that is a point of if it is clever or not. I think it will happen anyway.
It will happen.
It will happen.
We have to help that it doesn't hurt so much.
Yeah, exactly. This is the point. Yeah, the transition should be as smooth as possible. Otherwise, our societies will explode from a social point of view. Yeah, this is the point. Yeah, this technological level, what we have, it will not continue. We will not have it in 100 or 200 years. I'm really sure in this regard.
Technology is something that starts here and it doesn't have an ending for engineers. And if I thought something different, I would study technology.
Mm-hmm.
I really believe that technology has to surpass all this barrier somehow. That's what engineering
Yeah.
is.
So, a lot of problems.
I mean,
What?
society has tell us what they need, and we need to figure out how to get that in a sustainable manner. That's
Yeah.
engineering
But this is a problem, yes. The society is not telling up to now these things. Yeah. In Germany, due to this war in Ukraine, we have a kind of energy crisis. So prices are going up, and the people are very angry. Yeah, they have a lot of fear. So you see, the situation is very stupid. Sometimes in summer, we cool our apartments or houses, at least those guys who have an air condition, down to a temperature of 21 degrees. Yeah. In the winter time, we heat it up to 24 degrees sometimes. And now, in the moment, we are obliged to reduce our temperature to 19 degrees due to this energy crisis. And everybody is complaining, but it's totally stupid, yes, as Einstein said. He's not sure about the, if the universe is infinite, but the stupidity, maybe it is, yes. So in summer, I cool it down to 21. In winter, I need 24. Well, what is the problem to keep it on an average, rather low level, yes? You can reduce very easily, simply. My wife and me, we checked it out. During this year, we reduced our energy, and in summer it was warmer, of course, we don't have an air condition, but in winter, just now, we keep it on a level like 19 degrees. Or you can put a jacket in the evening when it's a little bit cool. And the funny thing is, everybody gets higher bills for the energy this year. We got money back. It was so simple, just to reduce by 2 or 3 degrees.
That's telling you that you can manage the behavior of people by, defining higher energy prices.
Yeah. In fact, this is just happening. Yes. Yeah, this is just happening. But then the people are on the road and they are aggressive. So this is, yeah, yeah. But maybe it's only a matter of time. Yes, maybe it was too fast. This change this year, but definitely it must come, and it takes time. And the people somehow have to learn that it is better for them to reduce some consumptions. Yeah. In fact, it's not a technological problem, or not primarily. It's a social problem, in fact, and a political problem.
We have to complain on the people working in the next building, humanity.
Yeah. No. Okay. Of course. Always we are saying all these stupid politicians, but the first thing is we have to blame first ourselves, and when we did this, then we can blame the others. Jörg.
I don't know, I miss the economics. They are producing a lot of problems.
Yeah, of course, they also have rethink some of their basic attitudes.
Because things are stupid products are produced because you earn money with it. They are senseless, but they earn money,
Yeah.
so they are produced. So that's something which is really, it's hard to have a free market on the one side, but to think about you should not do this because
Yeah.
it makes no sense for the future. So this is so hard to grab that and to control that. How would you do that?
Yeah, it's really. I think really we have to start to blame ourselves. I have to blame me. We are from Germany. Yeah, we are the rich people. Yeah, and we became rich since our economy produced a lot of stupid things. Yeah, in effect, who is guilty? In fact, I am guilty. Yeah. Yeah, this is the point, and this one has to learn, and everybody has to learn this. Yeah. Okay. It's a little bit philosophical, but okay. So maybe Hector, please give us a more positive viewpoint for the future. Hello?
Thank you. Thank you, Rainer. Okay. Speaking of Macs, he said Mac things.
Felipe.
We're trying to figure out how to use this Apple computer. So thank you for being here. Very interesting, the Professor Joff's point on the problem of having different things, that we have this energy there. But I would like to take that point and present the problem like it's on our transportation sector. I mean, there is, you just speak of electric cars, that somehow electric cars have a, I don't know, it seems to be the silver bullet for carbon neutralizing the transportation sector, which in Chile is like 40% of the energy. So that part of that piece of the chart is very difficult to decarbonize. So I would like to talk about two things. One is, I mean, the slides in Spanish for the sake of the people, but I'll speak in English. So we have this dilemma now on having a big campaign on producing hydrogen, green hydrogen, but on the other hand, we have electric cars. So there's something in between we're still not really certain about. So I would like to talk about this dilemma. So in Chile, we have a national strategy on producing hydrogen from renewable energies and sea marine water that we get from the ocean. You know, Chile is like a line in the map, so it's really easy for us to get water from the ocean. Reverse osmosis, we get water for the production, and then we are plenty of energy in the desert, for example, where it's like humongous amount of land for doing that with no other use. The desert is really dry, so there's basically no even life on the desert. So it's a really good place for building photovoltaics. And we have wind energy in the south. So there are very isolated places. We need the energy in the center of the country, so we wonder how to use those energies without these long distance transmission lines, which, by the way, are not really accepted by people. It's harder than before to build transmission lines. So there is sort of this national strategy on doing that. It's politics and everything, right? So there's some funding like for companies, but it's not really that significant. This is the piece of the chart I'm talking about, transportation. We're thinking of 2015 goals. You know, Chile has signed the agreement as well, the Paris Agreement. So they're trying to get the carbon out of the transportation matrix, and that's a problem. That's a problem, and some people have claimed that we can do that through hydrogen and hydrogen vehicles. Like hydrogen vehicles, it's something like some people do not really have a knowledge about, because we already have electric cars with a lithium battery. All the things that production of hydrogen is good for the country is that this is a energy agency picture on saying that Chile has a big potential, as I said before, in the north and in the south, and also the fact that the production cost it's a bit, well, this is projected. I mean, if we compute these things right now in Chile, they're about 3 something, right? It's not yet 1.4. It's something projected. So whereas the computations, like the projections now, said that even we are far from Japan, which is a country like calling people to sell their hydrogen in 2015. So all these people are thinking of Japan, Chile, for example, like also the US, but mainly Japan. So they figure out that even if it's a long distance, the production cost is lower, so it might be a good business. So there's all these things about hydrogen in Chile. So hydrogen is very simple in terms of how to use it for transportation. Basically, we are thinking of having 100% renewable energy matrix. We are like 30% by now by energy, with a lot of problems. So the idea is having this electricity grid, green, then we get the electricity from the grid, or maybe we can get the electricity like off-grid in some places, like I said before, in the north and in the south, where we are really abundant in resources, and we use this electrolyzer, which consumes electricity, and with water gives you the hydrogen. It's not that difficult. I mean, it's a big deal. This is a whole, I mean, I'm not a chemistry expert, but what you see, it's a box. You put electricity in, you put water in, and you get hydrogen out, and you get oxygen out. You use this hydrogen to fuel a car. It sounds reasonable. Carbon-free, 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 carbon-free. Like energy-wise, you see, but you have to build a car, and you spend like fuel on getting the materials for the manufacturing of the car. Yes, I'm agree. But energy-wise, it's carbon-free. It's got this car, instead of a battery, it's got something called a fuel cell, right? The fuel cell is very simple as well. You get hydrogen, right? The hydrogen is transforming to water, and in the chemical reaction you get electricity. The electricity is back to a electric motor. You can, power the car. You have a battery also, but the main reason for that battery is regenerative braking. So you get energy from the braking process back to the, the battery. But this battery is not as large as that of a regular electric car. So it's not that you are using two things instead of one, but that one is small, right? So that's an electric car based on a fuel cell. It's an electric car, but with a fuel cell instead of a large lithium battery. Well, let's get to real things. You have, this is 2017. It's not like now. It's somehow mature technology. It's something you can buy. And you see this, for example, some of the specs. You see the range. It's really interesting. It's a bit more than an electric car. Maybe it's like you take a look at the cars. They look like a regular car. You can have it in like sedan. You can have a suburban vehicle. You can have a compact. There are many. Like this is not something we're thinking of like a space shuttle for public transportation. It's something you can buy. At least these are prices in the United States. But it's something you can buy, not like it's mature in terms of technology. What are the cons? The price. You see like 60,000 US dollars. It's a pricey car. It's not. It's expensive car, right? So then you take a look at the prices, and here where society comes into game, right? I don't like that. I prefer the Porsche. The Porsche is a good-looking car. I sit down, I look at the window, and everyone is looking at me. I put the pedal, boom, it sounds like. This one, no sound, for example. The Tesla has its sound. There is a program, you put it on the car, and you see some roaring, noisy things. But they're not cheap. Because you take a look at similar cars, which are not hydrogen-based, but are the regular electric cars, and they're much inexpensive. You see like, not half, but close to half the price of a hydrogen car. So game over. I mean, you see, it's a good-looking car. It uses hydrogen. Hydrogen looks like the future, like the fuel that the space shuttles use. Oh, I want that. But you take a look at the prices. This one, carbon neutral somehow, because we get the electricity from the grid the same way we get the electricity for the electrolyzer. So they're both carbon neutral, but it seems that more mature, less expensive. So we prefer that one, right? So what I'm going to talk about is that sometimes when we pick a technological solution, you have to take a look at several aspects, not just the price of the vehicle, but in other things. And I would like to talk about this because these are some of the things we do study in my research group. So here's one thing. We in Chile, for example, have problems about the variability of resources. So basically, when you want to turn on the light, there is no wind, so you cannot turn on the light. That's like very simple. So if you have, for example, hydrogen, you can get the hydrogen with electricity. But there is something in between which everyone's talking about, which is storage, to store energy somehow. Well, if you store energy using batteries, like electrochemical processes, first, it's very expensive, very expensive. And second, the lifespan of storage is somehow on stage. For example, I have a friend of mine which is running a business on transportation, and he's got a fleet of vehicles in Valparaiso and Viña. You were there. And he's got a vehicle
fleet here in Santiago. You see the odometer, the number of kilometers that the two fleets have been used. They're about the same, but the battery of the ones in Viña del Mar are very more like degraded. Why? If they have been like the same trajectory in terms of kilometers. Tricky. Batteries are tricky. You cannot, let's say, buy a car and say, oh, the car would last 8 years. Who knows if it lasts 8 years? That's something really complex to assess from a business perspective, from societal perspective. Society wants simple numbers. The thing is, you can get the electricity for doing the electrolysis whenever you want. You want to do the electrolysis at night, you want to do the electrolysis during valleys of the electric consumption. And that is something really useful. So that, I would say, I'm not going to get much in deep into that, but the fact that you can use hydrogen and store it in a tank, like it's a piece of iron. A tank is a piece of iron. Well, I agree with you, it's like 700 bars of pressure to store the liquefied hydrogen, but that is something everyone has been done for like the 50s, because they liquefied nitrogen, liquefied everything. So it's a mature industry. And I'm telling you, because I study these things, it's much more inexpensive to have energy stored in a piece of iron than in an electrochemical process. Right? So maybe this car is more expensive, but this car it's cheaper. But take a look at the effects on the global energy metrics. And yeah, it's something like it's not that mature, but us energy analysts suggest it might be better to have hydrogen. Right? It's an open question. Well, a car, for example, what's another drawback of having an electric car? An electric car is something that consumes a lot of energy. So a regular house, let's say, 2,000 kilometers per year, it's like in Chile. In Germany, maybe it's not that much, but in Chile, we travel a lot. It's a long country. So we have like 20,000 kilometers per year in our cars. So an electric car consumes like 10 kilowatt hours per day, something like that. Is it that significant to you? It's a question. Is that significant in terms of having a car right next to your door in your house? It is significant in Chile because you consume like between 2030 and 2017 kilowatt per month. And you're going to have something that consumes 300, not right next to your door, consuming from the same place you are living now. So it's like having another house right next to your house. Energy speaking. If you speak about infrastructure, houses in Chile are from 3.5 to 10 kilowatt each. That's like the maximum power for a house. It's like 16 amps and 45 amps. So an electric charger can be from 2 to 22 kilowatt. So in terms of infrastructure, having a car in your house is like having another house, at least in Chile. Right? If you take a look at numbers in the US, for example, it's not that much because the energy consumption in a US house is much that in one in Chile. Like they consume like 400 or something. But even in the US, it's significant. It's half. And in a US regular house, you might have not just one car, but two. So the same effect. I am not thinking of having a fleet of buses running the city as we're now. I'm thinking of having 50% of the 5 million vehicles in Chile electric. I'm thinking of that because that's, the aim of the government. They want to be 100% carbon free. That's the solution they have, electromobility, right? So here's, for example, in Chile, there is this guy in a Chilean house, consuming an average of 200 kilowatts hour per month. And the guy now is having a taxi. He charges the taxi at home, and here is how his electric consumption has changed from 200 to 750 kilowatt per month. Significant. So here is a study in Australia. You mentioned Australia before. Australia is similar in terms of distribution in Chile. So see, if you have the substation zone, this large infrastructure with a lot of things like electric, so not a problem about integrating like 1,000 electric cars. Not a problem. You have these feeders, which are the street wires, the big ones. It's not a problem. But if you go to the transformer, that's the one on your house, but, well, we have overhead sometimes, mostly overhead distribution lines. You have underground transmission and distribution things, but it is the same. It's the fact that if you have 10 cars within your area, the 10 cars will collapse the transformer. 10 cars. And a transformer of this magnitude, right, it's for, let's say, 50 houses, 60 houses. So out of 60 houses, you are saying to people that only 11 of them will have the opportunity, with the infrastructure there, to have an electric car. Problem. The person, the 12th person will say, I want an electric car as well. Sorry, there's no room for you. Why? I'm paying the same for the network as you are paying. Why the 11th guy could install the thing and I cannot? How can you answer that? Super problematic. So here is Norway. Norway, you know, 50% of the car, it's being subsidized by the government. You buy an electric car, 50% of the price, boom, Norway gives you the money from the oil. Just saying. Just saying. So here is, well, we can think of that. But see what the projection, I mean, here's not the projection, is the sales. So more than 50% of new cars being bought in Norway are electric or plug-in hybrid. Interesting. So here is they foresee to have all the transportation, ships, marine ships, everything. Every vessel, every transportation, everything electric. And here is the demand. So Norway was 141 terawatt hour of energy in 2019, and they are projecting to have about 10,000 terawatt hour if they transform everything into electric. It's an order of magnitude in 40 years. Wow. Well, it's a projection they have. But here is the thing. How much money they have to invest in the transmission networks, distribution networks, and generation to make that possible? We're thinking of, well, billion here is not 1,000 million. It's a million of million, right? I mean, you use the same, right? When you say billion, it's a million of million. Yeah. It's a billion, a non-US million, I would say, a non-US billion. So this is a large amount of money. Who pays that? Who pays that? And other factor is that if people charge their things in the afternoon, it changes. Because everyone gets home and plug in the vehicle. The same thing happens with the air conditioning. It happens the same with the phone. It happens the same. So we have, I mean, I don't know sure in Germany, but Chilean peak hour is the afternoon, right? If somehow you see people, well, you can help the system and do not plug your electric vehicle, and when you get there, it might change. And if everyone charges at night, nothing happens. Society again. So societal choices make a big difference. Another one in the United States. So this is Boston Consulting Group. Was like 2 to 3 million clients, et cetera. They divided the way people behave in optimized, half optimized, and non-optimized, in the sense that if you get optimized, you charge your electric vehicle 50% off load at night and 50% mid-peak, which is mid-peak in US. In the US context, is like noon, something like that. 1.1 million EVs, 2013. They're thinking of 2,600 US dollars in upgrades for distribution. Means the having more capacity in your house. You have to install a new wire, for example. It includes the electric charger and everything. All the things you have to do electrically speaking to allow your house to have an electric car. So here is the thing. I mean, I'm not going to get into the details, but at the end, you are thinking of spending between $5,800 to $1,700 per year to maintain the network functioning, according to grid codes and everything. So if we are thinking of having our energy matrix and helping energy matrix through transportation matrix to be carbon free, we have to spend this money per vehicle per year, which leads to a 50% raise in the tariff. According to this study, it's like about 50% in the worst scenario, like the business as usual, people don't care about anything. In that scenario, you get 50% raise in the tariff, 50%. So people say, oh yeah, go install your cars, but you're gonna have 50% more expensive electricity tariff. They won't be so happy, right? So, just to sum up, to summarize, we know that hydrogen, it's not something like really technically speaking mature, right? But if we are thinking of, for example, using hydrogen to power our vehicles and make them carbon free, it will make a big difference in terms of the electricity grid. You have to think of the electric grid it will integrate also climatization, heating and cooling of the houses, heat pumps. Right? I'm into heat pumps. I have one in my house, my own. It works really good. It works really good. So where these heat pumps will get electricity from? The same place the electric cars will. So it's a, complex problem. So my perspective, being an electrical engineer, is that we have to try to help the electricity grid not to grow that much, because it's difficult to believe that the electricity grid will grow one order of magnitude. We're like fighting against variability and operational things in power system to get renewables integrated. And now we have to do the same, 100% renewable, and then 10 times larger. We have to try to help it somehow. And one thing can be helped is having hydrogen, green hydrogen, like with a massive role in vehicles. But it's up to the politicians. It's not up to us. So it's still something we have to discuss and try to think of. So electric vehicles are good. I like them. I don't have one of my own because my family is large. I'm father of 3, so we are 5. A 5-seat car is not enough for us. And in Chile, we don't have yet a large car for a large family, electric. I would definitely have an electric car. But thinking of having electric cars as a single silver bullet for solving the carbon neutrality of the transportation system and put that pressure on the electricity grid? We have to take a look. That's it. Thank you. Back to horses. Well, you wouldn't be here. You wouldn't be here. I mean, you take the aircraft. No? Please.
You showed in an impressive way that if we transform to a pure electric transportation system, you showed that it's a massive increase the electric grid, or you have to
Mm-hmm.
build a lot. And you talk about the H2 problem. So I wonder, I mean, it's the same that Reinhard said. I mean, the car is much more expensive now, the H2 car.
Mm-hmm.
Of course, I mean, it's still under development. There are not so many cars, not so much experience, so they are more expensive. I'm not so much into building these cars, but at least I read about building pure electric cars, and that also means you need a lot of resources like we sell in Earth. So, and these don't exist. We have a big problem again. So, I mean, it's not just electric grid, it's also how would you build all these cars? We have the next resource problem. I'm not sure about what's the point if we just build H2 cars. Do we have a resource problem too here? I don't know. Maybe we have to do that too. But so this is also a point which is coming up. I think it's even more than electric grid.
Yeah. I mean, in terms of hydrogen-based cars, I'm not really the expert for answering that. Like materials, I mean, I don't know what kind of rare or, as Reinhard said before, non-renewable materials they have. I'm not sure. But what I'm sure about is that an electric vehicle based on an electrical chemical battery, lithium, it's like the widespread use of the material that they use most. It's complicated to recycle. Lithium, it's a problem. So you're going to have millions of batteries changes in a yearly basis. Every year you're going to have like millions of those 200 kilogram things. How are you going to dispose of those things? The electrolyzer is much smaller, but I don't want to be imprecise. I don't have a clear picture of how is if there is a system for thinking of a renewable material, in a material sense, electrolyzer and fuel cell. I think it's something one should take about, but I'm not a chemical engineer. Please.
But I think as punchline, it goes very well together what you two said. I think it's us. We have to think about us, and we have to blame us, and we have to be ready to pay the price. And this is what you said. You said, hey, the electricity will be more expensive. Of course, that's not popular. If we don't do it, there won't be.
Yeah.
There's no future anymore. So we have to accept that things get much more expensive, and maybe our technology then goes
Yeah, I mean, it's a subtle question.
but I think if we just continue, like I want to have a cheap energy,
I mean,
it's tricky.
from my knowledge of people, like from my life, I would say that believing or blaming people for not doing the right thing for the collective of people is a rhetorical question. We know it's going to be like that. But what I think it works is when the governments get together and do a public policy on, taxing things we know are not good for the collective of people. I mean, that's it. I mean, I wouldn't see, like, in my mind, a scenario where people, like, suddenly became aware of the problem. I don't know, maybe Europe, there is some perception that that might happen somehow because of the educational level and things like that. But in Chile, I would say difficult. But if you have a strong government on these things, and they believe that this is something important, and they know it's going to be a problem, now, like 3 years of complaining, but you're going to have like 40 years of a new perspective on this matter, they just put the tax, and that's it. Oh no, it's bad. The tax will move. I don't know. For example, it would be a problem in the economy. Well, taxes are a problem for economists everywhere, but I don't find any other manner. It's carrot stick, and real changes have been. I mean, in the energy sector here in Chile, have a result. Are the result of a public policy like that. For example, catalyzers for inner combustion vehicles. You were forced to have them. I know people complain that. But after that, the city was, 10 episodes of emergency. Emergency means shut down because of pollution. Now, there are more cars, no emergency. There are like 3 or 4 episodes of like warning, oh, see that there's some smog on the streets. But the economy has not shut down since then because of the smog. And if you compute the amount of money that shutting down a city means, you see, oh, well done. 3 years of complaining pays off. Public policy, it's my answer to that. People will not, and from my perspective, just change their minds because they believe. You saw this movie on Netflix. It was Don't Look Up. Nice movie. It's a piece of teaching. That movie is a piece of teaching. You have to. I'm thinking of doing this activity with the students. You know, you are going to, for example, this room, and you show them a movie like that, and you stop and comment. Stop and comment. Stop and comment. Well, thank you for having me here and for listening to the presentation. And for those who are on the internet, we're happy for you to listen to the presentations, and we're happy also if you have questions, you are interested in these topics. There are many laboratories at university working on these things. Our lab, it's working on those type of questions. I'm an electrical engineer, so we like electrical engineering questions about the grid, if the grid is, etc. So thank you for your patience, and I would like you to see in another of the events of the faculty.